Okay, so we have a charge Q here and a variable charge big Q here. That's our test charge. We're gonna let it go from here to infinity. Okay. Now, in practical terms, we just let it go from here till it's far enough away that the force from this thing times the remaining distance becomes negative. Okay. And I didn't quite say that right. Well, was because we need to set up the interesting. Okay, so how much work is done on Q in the given increment? Given increment is an interval of length delta R, and R star is the coordinate at some point in the increment. I'm not going to be able to tell you the exact amount of work is done, or just where R star is in this increment, but it's taken to be such a small increment that it doesn't make much difference. And since we're going to take a limit as the delta R approaches zero when we do the integral, that the uncertainty of where R star is within the interval disappears. Okay. So how much work is done on capital Q given increment? Well, I'll call it delta W because this is just contribution to the work of an infinite number of these little increments. They're going to get infinitely small. Okay. But the amount of work done approximately equal to we wrote up from perpendicular to parallel. That just stands for parallel, the fourth parallel to our path times our delta R. Okay, well, what's the fourth? What's the fourth? Yeah, what's the fourth parallel to the path? Or the fourth parallel to the path? I have a little trouble with the fact that people can't tell me what that force is. Okay. I mean, we just done a chapter of Coulomb's law and another chapter of Gauss's law. Okay. Anyhow, it's a force. It's K times BQ little q over R squared. And this tells me that you're not thinking about what this means. You're memorizing it as a formula and you haven't thought through what it means. I'm not getting on you or anything. I'm just telling you, you're not going to get a good outcome unless you think about what things mean. And when you solve problems on the homework and whatever, in the text, you need to not have all the formulas sitting there in front of you. You have to pull them out of memory and make sense of them as you're working the problems. Okay. And that turned out to be a problem in the monoverbal calculus test too. I saw all kinds of evidence of people using formulas without understanding them, sometimes right, sometimes wrong. Okay. And I think that WebAssign there is maybe doing something a little similar to what Pearson materials do, is giving you a little too much help and not causing you to have to dig it out. Okay. So make sure you're digging it out, please. Okay, so anyhow, if you recall this out of your memory as many times as you should recall it out of your memory doing the problems you've been assigned, then you're not going to not know it. Okay, you might not think that this is it when you get here, but when we say, okay, it's just Coulomb's law, you got to know. Okay. You also have to think about with the direction of forces. It's along the axis. You don't know if it's positive or negative because you don't know what Q is, although we usually take it to be an arbitrary positive charge, okay? We usually think of this one as being a positive. I didn't say what this one's positive or negative, so the force could be this way or it could be that way. Right now, we're just doing that up there. It's not going to matter because when we get the expression, well, we already have the expression. Okay. If big Q is a positive charge, then this product is going to be positive if little q is positive, and negative if little q is negative. So our delta R, I did write the double arrow there. Our delta R is going to be in this direction. The delta R is actually okay. Right? So I'll just even call it a vector and give it a direction. It's in the positive R direction. Okay. Okay, well, that's the amount of work done in this input. Okay, except what's R down here? Not just any R. You have to evaluate this at a point, and we're trying to get the average force and call it up bar average on this interval, and that's where we use R star. Okay. Now, you need to be able to take this expression, think in terms of partition. Take partitioning the interval R naught infinity. Full increment. The delta R near Ri star. Well, so we're using the same delta R for practical purposes. If we're trying to do a simulation as quickly as possible, we would adjust the delta R's with distance and spend a little less computer time on the approximation. But since we're going to get an integral that we can easily do, don't bother. So right there is the amount of work done in the ith interval. Actually, I would go from one. I'm going to do from one to n, and I'm being a little sloppy. I don't want to get into the definition of this integral as the limit of integrals from R naught to some capital R, and then take the limit of that as capital R goes to infinity. That's how you do the proper integral. You should remember that. You should understand that. It's an important concept. It's going to be important, depending on what application you're trying to understand in your engineering or whatever. Okay, so I'm being a little sloppy here. You want to be able to fill in the slot. So actually, I'm not even gonna write limits in the sum. I'm just gonna say the sum, add them all up. Okay. And I'm gonna factor out K, big Q, little q. I'm not gonna factor out the delta R because we're gonna be taking a limit as delta R plus zero. And so you get this sum, which approaches then the integral down. There's your integral. You should understand this process. Basically, this turns into your integral, doesn't it? This is what you end up integrating. Your delta R kind of by magic becomes a dr, and your R star squared becomes an R squared because as you shrink all these intervals down to zero, your R stars become your R's, and your delta R's become infinitesimal drs. But details of this process, you should know this. And you're going to need to know it because you're going to need it in molecular calculus for short. You're going to get into intervals here. Okay, so now I'm going to need to. Okay, so do that integral. What's that integral? Give you about 2 minutes to do it. This is just kind of automatic. Straightforward. You have write this as the limit as big R goes to infinity of the integral. Write it a little bigger here. So see R naught to big R of K Q Q times big R over X squared. I have room to write the whole thing out, but we get A Q Q over R naught. So see that. I write about a little bit over here. And if your calculus, first year calculus isn't up to this, you really need to review. Especially if you want a variable, you'll see how to do all this. Okay, so the integral R naught to infinity. A with Q little q and dr over R squared is the limit. Big R of infinity of the integral from R naught to big R. A big Q little q That's DR over R squared, which is K big Q little q, which I'm probably should have acronymed to K. Times. Actually, uh, negative 1 over R. Evaluating R naught. Big R. And it's the limit. It's the limit as R is independent of this. And that is going to equal then A big Q little q times what? Negative 1 over big R minus negative 1 over R naught. Again, as low as R goes. Um, K, little q, big Q over R naught. And it's one of the most straightforward integrals you can do. Except for the exponential property, you have to do that in a minute. But that's an integral you should have done the type of numerous times. Okay. What is this? This is the work. Work done by a conservative force. And it's equal and opposite the change in potential energy. Okay. And again, you've heard me say this many times. I'm not sure it ever really sunk in. You really need it now. Okay. Change of potential energy is, by my definition, totally equivalent to the standard definition. Equal and opposite to the work done by conservative force. You're going to see that in multivariable within a couple of weeks also. If you're multivariable. Definition of conservative force is a gradient of potential function. And we're actually going to use that here because it's the last thing in the chapter summary. It's totally legitimate the way they present it. They're going to understand it as a simple gradient, which ought to be a very easy concept for you if you've had it in multivariable recently, which most of you have. And if not, you had it earlier. And I'll urge you to review it. Okay. So we come to the conclusion that here in a minute. We've got a charge little q here, a charge big Q here. Potential energy here. This is distance R. And well, potential energy here is, I'm gonna write K Q big Q over R. Is it K little q big Q over R? Or negative K little q big Q over R? Tell me positive, negative. Well, here's the work done by conservative force. Get it from here to here, right? Change of potential energy from here to here. Will therefore be, well, let's see, bottom between 2 points. Q from here to here. Okay. Go back to the concrete block. Lift a concrete block, let it go. Okay. It gains potential energy by virtue of having been lifted, right? Okay, so its potential energy here is higher than it is here. Makes sense? Okay. Now, in this case, where would you move it? From here to here or from here to here if you wanted it to fly back? Yeah, move from here to here. Because we're getting closer to this direction. Now let's assume that both these charges are positive. Okay. If they both happen to be positive, then it would have a greater potential energy here than here. Okay. Does it have a greater potential energy here or at an immense distance away? Greater potential energy here. If all these are positive. Okay. Now, if the charge is negative, then well, that could be negative KQ big Q over R. Okay. Because the negative is right there in the Q, right? Okay. So we go with a positive. It makes sense if the charges are both positive, that you have a greater potential energy here than there because you release this thing, gains kinetic energy as it flies away, right? So you need to reconcile all that. The integral is really easy. The work is really easy. Reconciling it in terms of the meaning, potential energy, you got to develop your intuition, not just follow formulas and examples. You got to pull it out of your intuition and wrestle with the idea until it becomes clear to you. Okay. I'm really tempted to abandon all online homework, but that's not. I'm going to supplement it with problems that make you pull things together rather than being led one step at a time if you choose to do so. I understand why you would do it. It's available. You've got limited time. You're under pressure, but it actually with the here's materials for people to use and work fairly well. That's I'm having real problems with webs. Okay. call this point B. Is potential energy per unit of test charge. This is a concept. You don't need this concept to imitate examples. Okay? You don't need this concept to use formulas, and if you happen to pull the right ones out, get this thing. But it's a concept that allows you to understand what's going on. Okay? So make sure you focus on these concepts that I taught. Make notes. It's potential energy per unit of test charge. Now, what's potential energy per unit of test charge? Potential energy is KQ BQ over R. Okay, again, I keep talking about, you want to think about what things mean at every point. This is an important thing. This is what we mean by electric or electrostatic potential, okay? Now, if you potential energy per unit of test charge, well, that's potential energy over test charge. Okay, little q big Q over R, want to write R squared there. Why is that? Speaking of stuff that makes it a little more difficult for me to do complicated analysis. That we really can. Not a formula to memorize, although you do want to memorize it. You want to memorize why this looks so much like, well, KQ over R squared. Where's that all like? Where's that all go together? It's not simple. Exception important. Okay, well, this is what it comes down to. Okay, now. Electric field is conservative, which is easy to prove. Just take its curl. Okay, and that's easy to calculate. Electric field, it depends if the electric field is reasonable. Electric field is conservative. Work from P to infinity is the same for any path. That's what a conservative field is. Okay. It's conservative if and only if the line integral, and we'll talk about line integrals. We'll wave our hands about line integrals here, but we're going to get our hands dirty with them molecular calculus. Okay. So we'll look at molecular calculus to refresh memory. Anybody who's had it and anticipate something's coming up soon. For those who have. Work from P to infinity is the same for any path. We're saying it's conservative. And this being it, only if it was just any path. And other ways of stating it. Should have written this. If and only P is a gradient of some potential function phi, then we'll put this as this is a potential function. Socrates got that property. Sometimes you see one, sometimes you see the other. Okay. This is really a foundational. The important thing is, since it's the same P to infinity on any path, doesn't matter how you choose to get them. So now, if we have two charges, one, two, we have some point P. This distance is R1. This distance is R2. What do you think phi would be at that point? We took a stab at it.
It's the same rate.
Was I recording when I did that? Did it? Oh, man. Let me just go over it again because I'm pushing up in the mind. Okay. Thought I was recording. I'm not sure I was. I need a bigger screen. I need it to be right about there. So I can see what I'm doing and I can tell where the things recording. Let's just make sure we've got this. Okay. So again, I think we did have the camera on. We made the analogy with lifting the block and releasing it. And basically it says, if this point is closer to this one, to a positive charge, then when you move closer, you're going to increase potential energy because when you release it, the repulsive force pushes this charge away and you get kinetic energy. Okay? So potential energy is higher here than it is here. Line extension, potential energy here, if everything's positive, is going to be greater than it is at infinity. If you come in from a great distance to here and then release it, it goes back to the great distance, it's going to gain kinetic energy because of the change in potential energy. So potential energy for the charge at this point is K big Q little K little q big Q over R. Okay. Now we define electric potential, which I use phi. It's a symbol. Okay, phi is a function of position. It's a function of x, y, z, or r theta phi. Okay, or r theta z, whatever coordinates we have been working in. It's a function of the position of this point. And the potential energy per unit of test charge, what would that be? That we discussed in a while. People kind of came out with it, but it's very straightforward. We divide the potential energy by the test charge. This requires only that we identify the test charge, which has always been big Q. And if you haven't incorporated that, again, you haven't been thinking about what things mean, and reasoning it out. Okay. So we divide this out, we get KQ over R. So we say that at the point P, phi, your electrostatic potential, which I'll call phi, is KQ over R. Okay, now I digress into some stuff that's review of what you've learned in multivariable calculus, if you haven't had it, and will learn within a couple of weeks. The rest of you who have it, field is conservative. First of all, if and only if it's a gradient of some potential function phi. Now, don't worry about that. Just talked about gradient last week. So if you got that function phi, you can do the gradient of that function. And you should by now have written the gradient operator so many times you can't possibly forget it. Work from T to infinity is the same for any path. Now, that's the big thing. A conservative field is path independent. Talked about that with gravitation, talked about that first semester. Path independence. You're going to see again in monovariable calculus. We saw when you took it, that what path independence means and how it all works together. Okay. Well, we can then say that the system consisting only of discharge, phi is KQ over R, where R is the distance from discharge and the point P. All right, now we're up to the point of, okay, now we got two charges. What's the potential? Okay, well, what's the net force on this? Well, net force is the net force you get from here, the force you get from here. Now I say, what's the net force? What's the net force on a test charge at this point? Okay. Hey, what's the net force as the test charge goes to infinity? The way the vectors go together and the fact that field is conservative ensures that the potential in P is potential due to Q1 plus potential due to Q2, which is just K Q1 over R1 plus K Q2 over R2. Okay. That can be proved. I could write it out, but read your book. It's pretty straightforward. Okay. It just comes down to the fact that at any point, the force is KQ1 over KQ1 Q KQ1 capital Q over R1 squared times the unit vector in the direction here to here. And the same thing for this. In the way those two go together, you can easily write out the symbols, do the integral, and everything separates out into the this plus this. Now I'm just waving my hands if you don't have time to do that. If it takes time to discuss this thing, you think about the concept. This is called by superposition. Superposition says that the force at any point due to this one plus the force at that same point due to this one is equal to the total force. Okay. Pretty intuitive concept. Okay, I want to go too far with that. Okay. Now, what are the units of the tension? What are the units of volume? So think about that for a second. Okay, put volume there should get the units. People, I don't think you got the right idea. Phi is what? It's potential energy per test charge, right? Now, of course, this is new. I think back to that, but look at the board. It's there. And what's potential energy? Where it come from? Well, we did the integral force times distance. Okay, so it would have units of newtons times meters, right? And of course, that's joules. 4 kilogram meters squared per second. Okay. So this is in joules. What's the test charge? Produce coulombs, right? Our joules per coulomb. Now, I forget where I was going with that. Because we got into the discussion. And I digressed a couple of times. But it's important to know that anyway. Um, Let me get my thought next. Totally forgotten where I'm going. There's some places I can go with this. Okay, so what's the work? Oh, I got it. Never mind. Another word for this is volt. We don't need a volt. Okay, so let's do just a quick example. What's the potential due to 1 microcoulomb at a distance of 60 centimeters? Well, 5 kQ over R. Make it plus 1 microcoulomb. So that's really easy to calculate, right? So it's 9 times 10 to the 9th Newton meter squared per coulomb squared times 10 to the negative 6 coulombs divided by 6/10 of a meter. I can't write that easy. This is going to give you approximately 10 to the 4th numerator. It's going to give you about 10 to the 4th, because this is almost 10 to the 10th. Then I'm going to divide it by 0.6. And it's going to give me something times 10 to the 4th. It turns out it's 1.5 times 10 to the 4th. Oh, sorry, times 10 to the 5th, which is 6. Wait a minute, no. 10 to the 4th. If that was a meter, it would be 10 to the 4th. And what are the units? Well, the meter divides the meter. Coulomb divides a coulomb. Coulomb squared divides a coulomb. And we get joules per coulomb. We're left with a coulomb in the denominator, a meter in the numerator. So it's a Newton meter over coulomb, which is joule. That's 1.5 times 10 to the 4th volts. we got half a coulomb at the 60 centimeter distance, how much energy does it take to move the 50 centimeter distance? Much more space. Looking. Well, work that out. What we just made it. There's some more space. Pause the video. Okay. George not quite sure. Just a little bit. Now, well, at 50 centimeters, you're just going to have a 0.5 in the denominator, right? And that's going to make the result 1.2 times greater. Zero 0.5. 3,000 volts. Now that seems like a lot. If we crank up that Wimshurst generator with those two little parallel circular plates up on the second shelf and the second to last bin to the right, we get 10 times that. Okay. In other words, well, to get a static electric discharge for an inch, it takes about 50,000 volts, depending on humidity and ionization up there and stuff like that. Okay, ionization. So delta phi is 3,000 volts. This 1,500 volt coulombs. Remember what a volt is? It's a joule per coulomb. Okay, 1,500 joule. Okay. Now 1,500 joules is a lot of energy. Well, if you think of moving 100 kilograms, which is a mass of a fairly big guy, okay? Or fairly big girl, fairly big person. About 50% more mass than I've got these days. Okay. You'd have to move that mass, which has a weight of about 2,200 newtons, almost a meter. Okay. So that's enough energy to lift a big guy 60, 70 centimeters. Okay. Fair amount of work, but it's a conceivable model. Well, when we get into circuits, you're going to have a potential difference between 2 points in the circuit. In lab, we did a lot of circuits with a 1.5 volt battery. Okay, that's 1.5 joules per coulomb between those points. And we were measuring currents up to the range of maybe 1/10 of an amp, which is 1/10 of a coulomb per second. Okay. To sort these ideas out, I really do recommend first of the introductory problem set. This deals about the units and stuff like that, how to reason out the units, and helps you sort out the relationships among these things. Now, you can sort it out from the text, but you need to sort it out. You need to be able to, at the very beginning, do those problems without having to look at the solutions. Now, it's fine if you look at the solution the first time, get down to the generalized solution, get it in your head, and come back to it the next day, so you can do another one the same way. So I kind of recommend it, but the Pearson materials, if you approach them correctly, will accomplish the same thing in a little less simple context. Okay, so anyhow, we have this electrostatic potential. If you want the electrostatic potential of a charge distribution, you integrate. And we're not going to do too much with that unless it's a static distribution. And now, let's say you have a wire here. By Gauss's law, you know the field at distance A is, let's say, a 1,000 meters per coulomb. Meters per coulomb over A. Your electric field needs to be in newtons per coulomb. A is going to be in meters. So if the meters in A divide this meters, the result is going to give us an electric field in newtons per coulomb, right? Now you know from Gauss's law that the form of this field is going to have a reciprocal of your distance, because area per cylinder and the charge enclosed and so forth. Well, that works together. Something you should be very familiar with, having done that chapter. Okay. I'm going to call it delta phi sub E. That's just what I've been using for delta phi, because we also have the magnetic potential function. Okay, but it's actually a vector potential. We'll see. You got delta phi to your electric field. Between P and Q. So here's P and here's Q. P is a distance R1. Q is a distance R2. What you have to do have to integrate from R1 to R2. along some path. Turns out this is going to just be your. Integral of 1/r dr. You don't have a reciprocal square here. You need to understand in terms of Gauss's law why you don't have a reciprocal square, why you have a reciprocal. Then you have a better feeling for this. This is going to lead to circular cylindrical capacitors. Important stuff. Okay. We do this in symbols. I choose to do it with a specific number here. The integral, which ought to be familiar to you, you're going to get 1/r is the natural log of r. It's going to be natural log of r2 minus the natural log of r1, which is the natural log of r2/r1. Okay, well, I recommend that you review the ideas and some of the results we've gotten here. Then read the text, work through everything. Okay? If you don't have a copy of the text, use the OpenStax text, chapter 1, electric potential. Okay? There it is. And get that done for next week. Got questions, email me.